the Neutron Physics Department of Centro Atómico Bariloche, Argentina, we have been developing new models for the interaction of slow neutrons with materials, particularly those of interest for cold neutron sources. Our aim is to produce scattering kernels and cross-section data for the corresponding energy range that can be used to explore new design concepts for compact cold neutron sources. The tremendous potential of neutrons as a proof of matter or as a research object by itself is limited by the relatively low flux intensity of the neutron sources as compared with photon sources. In addition, the different processes and devices reduce by several orders of magnitude the actual neutron intensity that eventually conveys the experimental information of interest. One of the research lines devoted to reduce part of those losses has been oriented to the search for efficient reflector materials that may improve the efficiency of guiding surfaces or the actual reflection of neutrons on containment walls to minimize their leakage. A large body of work has been done in the past, particularly concerning the interaction of slow neutrons with diamond nanoparticles. It has been demonstrated the high reflectivity of this material for ultra-cold neutrons and very cold neutrons, and proposed that such capacity extends at higher neutron energies, thus bridging the reflectivity gap in the neutron spectrum. We had proposed some time ago that magnesium hydride could be a very interesting material as reflector for cold neutrons by exploiting some unique features of the hydrogen in this system: large scattering cross-section, high number density, practically no translational motion within the metallic lattice, and unpopulated acoustic and optical modes at low temperatures. The latter dynamical characteristics imply a very large effective mass and therefore almost isotropic scattering, and a very small upscattering probability. We developed the scattering kernel for bulk diamond and powders of the nanodiamonds. First, we calculated the phonon density of states of diamond using ab initio algorithms. Then, we generated cross-section libraries over the thermal and cold neutron energy ranges using the codes enjoyed for the inelastic contributions and crystal for the elastic. In order to produce a library corresponding to diamond nanopowder, we used the experimental SANS results obtained by Teshigawara and co-workers. This structure factor can be integrated to give the scattering total cross-section corresponding to the coherent elastic effects caused by the nanopowder, which, when added to the nanosphere's bulk diamond contributions, produces the total scattering cross-section for this system with apparent radius of gyration of 2.5 nanometers. As I said before, we have proposed several years ago that magnesium hydride could be a very good cold neutron reflector, and so we revisited its cross-section data. We adopted a new frequency spectrum for obtaining a refined description of hydrogen in magnesium hydride, and then we calculated the components due to the metallic lattice and the hydrogen, employing again NJOY and crystal codes. The predictions of our calculations indicate that indeed the material could be a very interesting reflector for cold neutrons, thus reducing in a significant way the neutron leakage from a cold source. We performed reflectivity calculations in the same configuration used by Nesvishevsky et al., which is shown here, to compare the performance of both materials over the energy region of interest. Those results are displayed in this figure, indicating a predicted advantage of the magnesium hydride over the cold and thermal energy ranges. Same result as in the previous figure, but on an energy scale. Above about 10 to the minus 4 eV, the reflectivity of the hydride is larger than that of nanodiamonds. In particular, it is observed that this calculation seems to support such advantage over the cold and thermal regions. The effect of using those reflectors on a simple cold neutron source is displayed here. The geometry used to test the efficiency of nanodiamonds and cold magnesium hydride as reflectors is shown in this figure. The spectra of the outgoing neutron current from the cold neutron source is presented at the top right, and their ratio to the unreflected case at the bottom right. As expected, the use of a premodulator produces a significant improvement in the output of the cold neutron source, but little addition gain is observed when the nanodiamond reflector is introduced, except for the very cold neutron energy range. When the nanodiamond reflector is replaced by a layer of cold magnesium hydride, a significant increase in the cold neutron output is observed. Reports on those calculated results have been presented at recent meetings when we anticipated that at this stage it was necessary to perform proof-of-concept measurements to experimentally validate the predictions previously stated. For this purpose, Vesuvio seems to be an almost ideal instrument to simultaneously determine the transmission and scattering properties of diamond nanoparticles and magnesium hydride. Especially useful is the information produced by the two-dimensional transmission detector and the large angle detector bank. The DINS spectra is also very valuable to provide data on the hydrogen content of the detonated nanodiamond powder and the actual protonic density of the magnesium hydride sample. The samples for the experiments on Vesuvio were commercial powders. Special sample containers were used for the measurement at room and low temperatures. The actual density of the samples are indicated here, as obtained from the transmission data and the high energy normalization of the derived cross-section curves based on the known scattering lengths of the atomic species involved. This figure displays the two transmission measurements performed on the detonated nanodiamond powder at room temperature and nominal thickness of 4 mm and 7 mm. The Vesuvio instrument has a small bidimensional transmission detector, subtending a relatively large solid angle from the sample due to the short flight path between them. That means that a sizable in-scattering contributions may affect the transmitted flux in those cases when the sample material has a strong small angle cross-section. This is certainly the situation for our nanodiamond sample, and then we perform Monte Carlo simulations to evaluate the corrections using our evaluated scattering cross-section. In this figure, we show the geometry employed and the integrated flux map obtained. In this figure, we show our measured total cross-section of our nanodiamond sample. The red points are the corrected total cross-section of nanodiamond with a continuous line corresponding to the calculation using our model. This figure displays the two transmission measurements performed on magnesium hydride powder at room temperature and 20 K with a nominal thickness of 7 mm. These are the measured total cross-section of magnesium hydride at room temperature and 20 K, together with the calculated values according to our model. Now, this is a scheme of the Vesuvio experiment indicating the incident neutron flux, the transmitted and the reflected beams. The count rate C of theta and E from 132 detectors were recorded for each sample. The equation indicates the main contributions to those count rates. where phi of E times 1 minus transmission of E represents the source for the scattered neutrons. The factor R of theta E contains basically the reflecting power of the sample material. This is the ratio of count rates for the different backscattering detectors arranged in three triangular groups. We see here the ratio of count rate for the magnesium hydride and nanodiamond samples as the average of the three groups of backscattering detectors and for two different nanodiamond thicknesses. It is evident that such ratio depends on the thickness of the denominator. However, when we look for the ratio of R of theta E, it is clear that the result does not depend on the thicknesses, but essentially on the material. This is an important result which supports our proof of concept experiment. This shows typical cold neutron flux emerging from a liquid hydrogen source, and this is shown in the black line and dots. And the ratio of reflectivities between cold magnesium hydride and nanodiamond, that is the red line. The dashed red line represents the expected trend of the reflectivity ratio in the cold neutron region. So we arrive to our conclusions. We have developed and validated a slow neutron cross-section library for nanodiamond powder and magnesium hydride at room and cryogenic temperatures. We perform Monte Carlo simulations to compare both materials in terms of their capacity as slow neutron reflectors. Those calculations confirm the good performance of nanodiamonds in the very cold neutron region, whereas magnesium hydride displays a great performance as a reflector for cold neutrons. The set of experiments were performed at the Vesuvio ISISS instrument to measure the cross-section of nanodiamond powder and magnesium hydride. Perform transmission measurements in order to determine the total cross-sections for those materials. Careful analysis of the in-scattering contributions were also included in order to obtain a reliable total cross-section information. The ratio of the backscattering spectra from both materials indicates the better performance of the hydride over the energy region explored in the experiment. We confirm, therefore, that magnesium hydride at low temperatures can be used with great advantage as a reflector for cold neutron sources, in particular for those cases of large surface to volume ratio. Wish to indicate that the experimental results presented here were also presented recently in a virtual conference, which was a kind of preliminary conference of UCAN's 9 meeting to be held in Japan later this year. It's a pleasure to acknowledge the valuable help of Dr. Giovanni Romanelli and Goran Skoro from the ISISS facility in England. And finally, I just want to tell you that very important announcement. The ICNS, the International Conference of Neutron Scattering, originally scheduled for 2020, has been postponed, and the new date is now 21 to 25th of August 2022. That is going to be in Buenos Aires next year. So it will be a pleasure to have you visiting here in Argentina. So thank you very much.